the #1 technological tragedy of our time. Those were the words President Richard Nixon used to characterize something that had just happened in the halls of Congress. Not a military defeat, not an industrial collapse, but rather the votes that stopped funding for an American supersonic transport. It was March 1971, and with those congressional votes, a dream that had captivated the nation seemed to die. The Boeing 2707, America's answer to the Concorde, would never fly. The prototypes would never be completed. The future of faster-than-sound civilian flight in America appeared to be over before it had truly begun. But sometimes, endings are really just transformations. Sometimes what looks like failure becomes the foundation for something more profound. Because despite the cancellation of the supersonic transport program, the work didn't completely stop. The knowledge gained, the theories developed, the wind tunnels built, the researchers trained, all of this represented too much value, too much potential to simply be abandoned. The White House, the Department of Transportation and its Federal Aviation Administration, and NASA, with help from some sympathetic members of Congress, made sure that the progress in supersonic technologies wouldn't completely dissipate into nothing. During 1971 and 1972, even as the wreckage of the SST program was being cleared away, the Department of Transportation and NASA quietly allocated funds for completing some of the research and experiments that were already underway when the program was terminated. These weren't massive investments, they weren't front-page news. But they represented something important, a belief that the problems of supersonic flight, particularly the challenge of the sonic boom, weren't insurmountable. They were simply difficult, and difficulty had never stopped American aerospace research before. The administration took things a step further. They added line-item funding to NASA's fiscal year 1973 budget specifically for scaled-down supersonic research, with a particular emphasis on the environmental issues that had been raised so loudly and so effectively during the SST program debates. The sonic boom had been weaponized by opponents of the SST, used as a symbol of everything that was wrong with technological progress that didn't consider its impact on ordinary people. If supersonic flight was going to have a future, the boom would have to be addressed seriously, scientifically, and systematically. In response to this directive and this opportunity, NASA established what they called the Advanced Supersonic Technology Program in July 1972. It was a new beginning, emerging from the ashes of the old dream. And with it began what would become a half-century pattern of on-again, off-again efforts to solve the problems of faster-than-sound civilian flight. Through all the iterations, through all the name changes and budget cuts and political headwinds that would follow, one challenge would remain stubbornly persistent, perhaps the most difficult of all: the sonic boom. The dance of acronyms and political reality. The program that launched in 1972 as the Advanced Supersonic Technology Program, AST for short, was born into a politically sensitive environment. The ink was barely dry on the congressional votes that had killed the SST. Environmental awareness was rising across America. The first Earth Day had been celebrated in 1970. The Environmental Protection Agency had been created that same year. People were questioning technology, questioning progress, questioning whether faster was always better. NASA understood this. They understood that perception mattered, that names mattered, that anything that looked like they were trying to build another SST through the back door would be dead on arrival. So to indicate more clearly the exploratory nature of this effort and allay fears that it might be a potential follow-on to the cancelled SST, the overall AST program was renamed in 1974. The new name was Supersonic Cruise Aircraft Research, giving us the acronym SCAR. The word research was emphasized. This wasn't about building a plane. This was about understanding the science, developing the technology, creating the knowledge base that might, someday, perhaps enable someone else to build a plane. But even that wasn't careful enough. The term aircraft in the program's title continued to raise suspicion in some quarters. Critics worried that the goal might be some sort of prototype, that research was just a cover story for development. So NASA shortened the program's name again in 1979, not long before the program's demise. Now it was simply Supersonic Cruise Research, SCR. No aircraft, just cruise, just research. For the sake of simplicity, this latter name is often applied to all 9 years of the program's existence, though it went through these 3 distinct identities as it tried to find a politically acceptable way to exist. To NASA's leadership, the principal purpose of the AST/SCAR/SCR program was straightforward, regardless of what it was called. They wanted to conduct and support focused research into the problems of supersonic flight while advancing related technologies. It was more modest than the SST program had been, more focused, more careful. But in its own way, it was ambitious. As with the SST program, though on a smaller scale, NASA's aeronautical centers, most of the major airframe manufacturers, and many research organizations and universities participated in this ongoing effort. From Washington, NASA's Office of Aeronautics and Space Technology provided overall supervision, but they understood that the real work, the detailed day-to-day management, needed to happen at one of NASA's centers where the expertise and facilities existed. They delegated that management to the Langley Research Center in Virginia, which established an AST project office within its Directorate of Aeronautics. Soon this office was placed under a new organizational structure called the Aeronautical Systems Division, reflecting Langley's commitment to treating this as a serious long-term endeavor. The program was organized into several major elements, each addressing a critical aspect of supersonic flight. There was propulsion research, looking at the engines that would power these future aircraft. There were studies of structure and materials, trying to understand how to build airframes that could withstand the unique stresses of sustained supersonic flight. Researchers investigated stability and control issues, trying to understand how these aircraft would handle. They studied aerodynamic performance, trying to squeeze every bit of efficiency out of designs that were fundamentally fighting physics. And they worked on airframe propulsion integration, trying to figure out how to marry engines and airframes in ways that worked at both subsonic and supersonic speeds. NASA spun off propulsion work on something called a variable cycle engine as a separate program in 1976. This was a sophisticated concept, similar to a conventional mixed-flow turbofan, but with an additional secondary outer duct that could increase the overall bypass ratio and thus the airflow handling capability that was particularly desirable at very high speeds. It represented the kind of advanced thinking that characterized this era of aerospace research. Within all these major elements, sonic boom research occupied a specific but important niche. It fell under the umbrella of aerodynamic performance, but it was just one of 16 AST sub-elements. This reflected a practical reality. The sonic boom was important, but it was only one of many challenges that a successful supersonic transport would need to overcome. Fuel efficiency, range, passenger capacity, takeoff and landing noise, structural weight, maintenance costs, all of these mattered too. The sonic boom couldn't consume all the resources, even though it was, in many ways, the most publicly visible problem. At Langley's Aeronautical Systems Division, several key figures emerged as the leaders of this effort. Cornelius Driver, who everyone called Neil, headed the Vehicle Integration Branch. F. Edward McLean, a brilliant aerodynamicist, served as chief of the AST Project Office. These two men were instrumental in planning and managing the AST SCAR effort through most of the 1970s. When McLean retired in 1978, the AST project office passed to another skilled aerodynamicist named Vincent Massitti, while Driver took over leadership of the entire Aeronautical Systems division, reflecting his broader expertise and management capabilities. 1 year later, in 1979, Dominic Maglieri replaced Massitti in the AST project office. Maglieri brought deep expertise in sonic boom research to the position, but by the time he took the role, the goal of minimizing the sonic boom for overland crews had long since ceased being an SCR objective. The program's focus had shifted, responding to regulatory reality and political necessity. As McLean would later explain with admirable clarity, the basic approach of the SCR program was to search for solutions to supersonic problems through disciplinary research. Most of these problems were well known, but no satisfactory solution had been found. When the new SCR research suggested a potential solution, the applicability of that suggested solution was assessed by determining if it could be integrated into a practical commercial supersonic airplane and mission. If the potential solution could not be integrated, it was discarded. This was engineering pragmatism at its finest. Beautiful theories and elegant mathematics meant nothing if they couldn't be embodied in metal and composite materials, if they couldn't survive the harsh realities of commercial aviation operations, if they couldn't be built within reasonable cost constraints. The goal was practical progress, not academic papers alone. The rule that changed everything. To meet the practicality standard for integration into a supersonic airplane, the scientists and engineers trying to solve the sonic boom problem had to clear a new and almost insurmountable hurdle. This hurdle appeared less than a year into the AST effort, and it fundamentally altered the trajectory of supersonic research in America for decades to come. In April 1973, responding to concerns that had been raised loudly and repeatedly since the SST program debates, the Federal Aviation Administration announced a new rule. It would be effective on September 30th of that year. The rule banned commercial or civil aircraft from supersonic flight over the landmass or territorial waters of the United States if measurable overpressure would reach the surface. Read that again carefully. If measurable overpressure would reach the surface. Not if it exceeded some threshold. Not if it caused damage or significant annoyance. If it was measurable at all. This was essentially a complete ban on civilian supersonic flight over American soil. The FAA had looked at the public opposition to sonic booms, looked at the political environment, looked at the technical challenges of boom reduction, and decided that the simplest solution was prohibition. They would protect American citizens from sonic booms by ensuring those citizens never experience sonic booms from civilian aircraft. Problem solved, at least from a regulatory standpoint. One of the initial objectives of the AST program's sonic boom research had been to establish a metric for public acceptability of sonic boom signatures that could be used in the aerodynamic design process. Researchers wanted to understand what level of boom could people tolerate. Was it a matter of peak overpressure, duration, rise time, the shape of the signature? If they could establish acceptable thresholds, they could design aircraft to meet those thresholds. It seemed like a rational, engineering-based approach to a human problem. The FAA's stringent new regulations seemed to rule out any such flexibility. There would be no acceptable threshold because there would be no booms, period. This forced a fundamental reassessment of priorities within the AST SCAR program. If supersonic flight over land was impossible under American regulations, what was the point of extensive research into boom minimization for overland crews? The resources could be better spent elsewhere. As a result, when Congress cut fiscal year 1974 funding for the AST program from $40 million down to about $10 million, a 75% reduction that reflected continuing skepticism about supersonic research, the sub-element for sonic boom research went on NASA's chopping block. It wasn't eliminated entirely, but it was dramatically scaled back. The priorities shifted. The design criteria for the SCAR program became focused on a different kind of airplane. A 300-foot-long, 270-passenger aircraft that could fly as effectively as possible over land at subsonic speeds, or possibly low transonic speeds, yet still cruise efficiently at 60,000 feet and Mach 2.2 over water. This was the compromise position. The aircraft would take off and climb out subsonically over American cities. It would accelerate to supersonic speeds only after reaching ocean waters. It would cruise supersonically across the Atlantic or Pacific, then it would slow down again before reaching foreign shores, or at least before reaching populated areas. It could work, in theory, but it meant accepting that the sonic boom problem hadn't been solved. It had been avoided. To meet these less ambitious criteria, Langley aerodynamicists pulled out some of their older work. They took their SCAT 15F design from the late 1960s. SCAT stood for Supersonic Commercial Air Transport, and modified it into a notional concept with better low-speed performance. They called this modified design the ATF 100. The trade-off for better low-speed performance was higher sonic boom potential, but that didn't matter anymore since the aircraft wouldn't be flying supersonically over land. This ATF 100 served as a baseline for 3 industry teams who would develop their own designs based on the new mission profile. The dreams had been downsized, the scope had been reduced, but the work continued. And even though sonic boom minimization was no longer a primary objective, the research into boom physics, boom propagation, and boom reduction didn't stop entirely. Because researchers understood something that regulators and politicians perhaps didn't. Regulations can change. Technology advances. What seems impossible today might be achievable tomorrow. And when that tomorrow came, someone would need to have done the homework. The evolution of boom theory. Back when the AST program began in 1972, prospects for significant quieting of supersonic aircraft's sonic footprint for operations over land still appeared possible. The regulatory hammer hadn't fallen yet. The future looked more open. And sonic boom theory had advanced significantly during the 1960s. Some promising ideas for reducing boom signatures had begun to emerge from the theoretical work and wind tunnel experiments that had been ongoing. These endeavours continued to bear fruit into the early 1970s, even as the political and regulatory environment was shifting against them. Science doesn't stop just because policy changes. Researchers kept thinking, kept calculating, kept testing, because that's what researchers do. And some of what they discovered would prove valuable years or even decades later. As far back as 1965, NASA's Ed McLean had predicted something remarkable. He suggested that the sonic boom signature from a very long supersonic aircraft flying at the proper altitude could be non-asymptotic. That's a technical term with profound implications. It means the boom wouldn't reach the ground in the form of the typical N wave that characterized most sonic booms. Instead, the pressure signature might retain a different shape, potentially a less disturbing shape, all the way to the surface. This was a stunning theoretical insight. For years, researchers had assumed that N waves were inevitable, that the physics of shockwave propagation through the atmosphere would always steepen and sharpen the pressure waves into that characteristic double bang signature. McLean was suggesting that under the right conditions this might not be true. The implications were enormous, even if the practical requirements, a very long aircraft flying at precisely the right altitude seemed daunting. The most radical ideas for achieving this involved lengthening an aircraft by projecting what researchers called a phantom body, using something like a heat shield extending far ahead of the actual aircraft. These concepts continued to be set aside as impractical. The engineering challenges were simply too severe. But another idea, projecting a long extension from the aircraft's nose to slow the rise of the bow shockwave, would eventually prove more realistic. Sometimes the difference between genius and foolishness is just a matter of which problems you can actually solve. Most of the ongoing research on sonic boom minimization tended to follow the general course set by two brilliant researchers named Albert George and Richard Seabass. In 1971, they had published a landmark treatise that fundamentally changed how people thought about sonic boom reduction. Their work represented a major conceptual advance, moving beyond simple rules of thumb and into rigorous mathematical analysis of what was possible and what wasn't. George and Seabass went into more detail about their sonic boom minimization concepts during the next few years, refining their mathematics, testing their predictions against wind tunnel data, exploring the implications of their theories. This work culminated in October 1974 with the publication of a paper titled "Design and Operation of Aircraft to Minimize Their Sonic Boom" in its final form. By then, the work wasn't especially relevant to the AST program anymore, since overland supersonic operations were no longer part of the program's objectives. But it marked another crucial milestone in the development of sonic boom theory, a milestone that would matter later, even if it didn't seem to matter immediately. The paper by George and Seabass tackled a fundamental problem. There was no accepted standard on what should be reduced or minimized to make the sonic boom more acceptable. Was it the peak overpressure, the total impulse, the rise time of the shock wave, the duration of the overpressure? Different metrics might lead to different optimal designs. So George and Seabass considered remedies for treating each of the boom symptoms individually, exploring the mathematical relationships and trade-offs involved. Their analysis was based on common assumptions such as an isothermal atmosphere, a standard formula for how air temperature and density change with altitude that simplified the mathematics considerably. It was premised on the supersonic area rule, that elegant principle that related the distribution of volume and lift along an aircraft to the strength and shape of its shock waves. Using these foundations, they examined how to shape the equivalent body of revolution for the vertical plane to minimize various signature parameters below the aircraft. The equivalent body of revolution was a concept that had been around for a while. It was a way of representing a complex three-dimensional aircraft shape as if it were a simpler body of revolution, like a carefully shaped football or rocket that would produce the same shockwave pattern. This mathematical simplification made the optimization problem tractable, turning the design of an entire aircraft into the design of a smooth area distribution curve. In addition to the obvious approaches of reducing overpressure and impulse by lowering aircraft weight and improving efficiency, better lift-to-drag ratios, better thrust-to-weight ratios, George and Seabass looked at specific aerodynamic design principles. They cited key findings from the growing literature on the topic while presenting their own original remedies and insights. They were building on the work of others while pushing the boundaries further. By way of creating general rules to be considered in aircraft design, George and Seabass showed mathematically and graphically the relationships and trade-offs between various aircraft design features and sonic boom characteristics. For example, they demonstrated that higher Mach numbers could somewhat lower impulse but wouldn't reduce peak overpressure. This was useful information for designers trying to choose optimal cruise speeds. They calculated and described how the proper combinations of shape, weight, length, and altitude, cruising lower than previously thought optimal, could practically eliminate the explosive sound of the bow shockwave. This didn't mean the signature would be silent and the total overpressure would still be significant, but the sharp crack at the front of the N wave could be softened into something more like a gradual pressure rise. Thus, for example, a Mach 2.7 aircraft weighing 600,000 pounds with a length of 300 feet could have a shock-free, though certainly not silent signature at altitudes below 30,000 feet. They also examined various operational techniques mathematically. What transonic speeds would prevent sonic booms from reaching the ground at all? At the other extreme of the speed range, they predicted that hypersonic speeds, Mach 5 and beyond, might help with lowered shock waves but wouldn't solve other problems, especially impulse. The total momentum transfer would still be substantial. They concluded that aircraft could be designed to achieve overpressure levels just below 1 pound per square foot for both the positive and negative phases of the pressure signature, with impulses of about 1/10 of a pound-second per square foot. These numbers weren't too different from the sonic boom generated by the Air Force's SR-71 Blackbird, and experience with SR-71 overflights should give some indication of whether overpressures and impulses of this magnitude would prove acceptable to the public. Unfortunately for the future of supersonic transports, the public's apparent tolerance of occasional sonic booms from the Air Force's small fleet of SR-71S, dramatic aircraft on important military missions, did not transfer to the more frequent booms that scheduled supersonic airline traffic would generate along their routes. People would put up with a lot for national security. They were less willing to put up with it for someone else's faster business trip. Although most of Seabass and George's work at the time applied to large transports, the kind of aircraft that the SST program had envisioned, their analysis of various types of airframe shaping to alter the formation and evolution of shockwaves proved broadly applicable. For example, they showed that slightly blunting the nose without significantly penalizing performance could help. This kind of insight would be relevant to smaller supersonic aircraft as well, not just jumbo jets. Based on their insightful analyses, their rigorous mathematics, and their practical approach to what could actually be achieved, George and Seabass are justly considered the fathers of sonic boom minimization. They didn't solve all the problems, but they defined the problems clearly, showed what was theoretically possible, and provided the mathematical tools that others could use to explore designs. That's what great scientific work does. It opens doors for others to walk through. The computational revolution begins. Meanwhile, other researchers working under contract to NASA continued to advance the state of the art in different directions. Antonio Ferri of New York University, partnering with Hans Sorensen of the Aeronautical Research Institute of Sweden, used new three-dimensional measuring techniques in Sweden's trisonic wind tunnel to more accurately correlate near-field effects with linear theory. They were testing a model representing a 300-foot-long SST cruising at Mach 2.7 at 60,000 feet, and their measurements projected sonic booms of less than 1 pound per square foot, right in line with what the theory suggested was achievable. Ferri's death in 1975 at the age of 63 left a significant void in the field of supersonic aerodynamics, including sonic boom research. He had been one of the giants, someone who combined deep theoretical understanding with practical engineering sense. His loss was felt throughout the community, a reminder that progress depends on individual people with unique insights and capabilities. But even as some contributors were lost, new capabilities were emerging that would transform the field. In addition to theoretical refinements and improved wind tunnel techniques, important new computer modeling capabilities continued to appear in the early 1970s. These would eventually revolutionize how sonic boom research was conducted, though in the mid-1970s they were still fairly primitive by later standards. In June 1972, Charles Thomas of the Ames Research Centre published details on a computer program he had developed called the waveform parameter method. This program used new algorithms to extrapolate the evolution of far-field N waves from near-field measurements. It offered an alternative to using what researchers called the F function, the pattern of near-field shock waves emanating from an airframe, as required by a program developed by Wallace Hayes and colleagues at Princeton's Arup Corporation. Both methods, Thomas's and Hayes's, accounted for acoustical ray tracing through the atmosphere. Both would arrive at almost identical results when properly applied, but Thomas's code offered some practical advantages. It allowed for easier inputs of wind tunnel pressure measurements, and it could handle various input parameters like Mach number, altitude, flight path angle, acceleration, and atmospheric conditions through automated data processing. This made it much more user-friendly for routine engineering work. Both Thomas's waveform parameter program and Hayes's Arup program remained relevant well into the 21st century, a testament to how well they captured the fundamental physics, as one expert in sonic boom modeling would explain 30 years after Thomas released his program. Both are full implementations of fundamental theory, accounting for arbitrarily maneuvering aircraft in horizontally stratified atmospheres with wind. Moreover, virtually every full ray trace sonic boom program in use decades later evolved in one way or another from one of these two foundational programs. This was the early promise of computational fluid dynamics applied to sonic boom prediction. The programs couldn't design aircraft by themselves. They couldn't optimize shapes automatically, but they could take proposed designs and predict what their sonic booms would sound like with much greater accuracy than previous methods. This capability was essential for making progress. You can't improve what you can't measure, and you can't measure what you can't predict. In June 1973, at the end of the AST program's first year, 3 researchers from Langley, Harry Carlson, Raymond Barger, and Robert Mack, published a study on the applicability of sonic boom minimization concepts for an overland supersonic transport. Their work was based on what they called the airplane design philosophy, most effectively presented by Antonio Ferri, in which sonic boom considerations played a dominant role in shaping the entire aircraft design. They examined 2 baseline AST designs and 2 reduced boom concepts. The objective for all 4 designs was a commercially viable Mach 2.7 supersonic transport with a range of 2,500 nautical miles, precisely the coast-to-coast distance across the United States. They were still thinking, in mid-1973, about overland supersonic flight in America, even though the regulatory writing was already on the wall. Applying the experimentally verified minimization concepts developed by George, Seabass, Hayes, Ferri, Barger himself, and L.B. Jones, and using the ARAP computer program to propagate shock waves through the atmosphere, Carlson's team explored various ways to manipulate the F function to project a quieter sonic boom signature. As with similar previous efforts, their options were limited by a fundamental gap in knowledge. There was no established set of signature characteristics, combinations of initial rise time, shock strength, peak overpressure, and duration that people would tolerate, both outdoors and especially indoors, where booms would penetrate walls and windows. The complexity of aircraft geometry made measuring effects on tail shocks particularly difficult. The interaction of shock waves from the nose, wings, engines, and tail created intricate patterns that were hard to predict with complete confidence. So they settled on a simpler objective: lowering peak overpressure, with the goal being a plateau or flat-topped signature rather than the sharp N wave that most supersonic aircraft produced. Considering this objective along with numerous other parameters deemed necessary for a practical airliner, passenger capacity, fuel efficiency, structural weight, stability and control, takeoff and landing performance. Their study confirmed several design principles. They found advantages in highly swept wings located toward the rear of the fuselage, with carefully designed twist and camber for sonic boom shaping. The sweep angle affected how shockwaves formed and propagated. The rearward location helped keep the lift distribution favorable for boom reduction. The study also confirmed the benefits of using canards, small airfoils placed near the nose of rear-winged aircraft that served as horizontal stabilizers, and positive dihedral wings that angled upward from the fuselage. These features helped optimize lift distribution specifically for sonic boom benefits, not just for aerodynamic efficiency. Two of their designs showed particular promise. One used a delta wing configuration, the other an arrow wing. Both showed bow shocks of less than 1 pound per square foot at an optimum cruising altitude between 53,000 and 59,000 feet. But the report included an important caveat, a recognition of how much remained unknown. There could be no assurance at this time that these shock strength values, even if attainable in a real aircraft, would permit unrestricted overland operations of supersonic transports. Would the public accept even these reduced booms? Nobody really knew. The research needed to answer that question, systematic studies of human response to various boom signatures, wasn't being done in the United States on any significant scale. And without that knowledge, designers were working blind, trying to hit a target they couldn't see. In October 1973, Edward Kane of Boeing, who had been a key sonic boom specialist during the SST program, released results of a similar NASA-sponsored study. He looked at the feasibility of a commercially viable low-boom transport using technologies projected to be available in 1985. Still more than a decade away at that point. Boeing explored two longer-range concepts: a high-speed Mach 2.7 arrow wing design that would produce a sonic boom of 1 pound per square foot or less at 55,000 feet, and a medium-speed Mach 1.5 highly swept wing design with a signature of ½ pound per square foot or less at 45,000 feet. The slower design was particularly interesting. Mach 1.5 was at the low end of what you'd call truly supersonic, barely faster than the speed of sound by the standards of the SST program. But it offered some advantages. Lower speed meant lower boom intensity. It meant less severe heating and structural requirements. It meant better fuel efficiency, and for many city pairs, a Mach 1.5 aircraft could still offer significant time savings over subsonic jets. Ironically, these results were published just as the new FAA rule rendered them largely irrelevant. The ban on measurable sonic booms over the United States meant that neither the Mach 1.5 nor the Mach 2.7 designs could operate as intended on domestic routes. In retrospect, this Boeing study represented a final industry perspective on the prospects for boom minimization before the SCAR program officially dropped plans for supersonic cruise over land. It was the end of an era, though few recognized it as such at the time. Obviously, the FAA's virtual ban on civilian supersonic flight in the United States dampened any enthusiasm by the major aircraft manufacturers to continue investing substantial capital in sonic boom research. Boeing, Lockheed, McDonnell Douglas, these companies would continue participating in the SCAR program on government contracts, but their internal investment in boom research dried up quickly. Why spend money developing solutions to a problem that regulation had made irrelevant? Within NASA, funding for academic studies of sonic booms slowed to a trickle, and many NASA employees with experience in sonic boom research redirected their efforts into other areas where they could have more immediate impact. Of the approximately 1,000 technical reports, conference papers, and articles by NASA and its contractors listed in bibliographies of the SCR program from 1972 to 1980, only 8 dealt directly with the sonic boom. 8 out of 1,000. That tells you everything you need to know about how priorities had shifted. The digital dawn. Even so, some foundations were being laid that would benefit future sonic boom research, even if the immediate applications weren't obvious. Of great benefit to supersonic aerodynamics and other aeronautical endeavours, NASA was fostering the development and use of powerful new digital computer capabilities that went far beyond the specialised boom prediction codes. In early March 1975, the Langley Research Centre hosted a major conference titled Aerodynamic Analyses Requiring Advanced Computers. It was a gathering of researchers who were pushing the boundaries of what digital computation could do for aerospace engineering. In introductory remarks, J. Lloyd Jones, NASA's Deputy Associate Administrator for Aeronautics Technology, extolled the advances made since NASA's last aerodynamics conference in 1969. Just 6 years earlier, but it might as well have been a generation in computer terms. Rather than having to rely on simple shapes and various mathematical shortcuts to formulate solvable equations, usually involving only 2 dimensions, researchers were now able to calculate complex phenomena like transonic mixed flows with embedded shock waves and flows around complex wing-body configurations in 3 dimensions. The future promised much greater improvements. Dean Chapman of the Ames Research Centre discussed the accelerating advances in the digital modelling and analysis capabilities of computational fluid dynamics, CFD for short. CFD, Chapman asserted, offered tremendous potential for revolutionising the way the aerospace profession had been doing business. This wasn't hyperbole. With the expected arrival of supercomputers, he envisaged CFD overcoming the inherent limitations of wind tunnels and eventually allowing timely processing of heretofore virtually unsolvable differential equations governing fluid flows over solid surfaces, with the full effects of friction included. The mathematical foundations of CFD went back centuries. The brilliant 18th century mathematician Leonhard Euler had devised nonlinear partial differential equations governing the momentum, velocity and pressure, and the continuity of flowing fluids. But Euler's momentum equation didn't account for the viscous effects of friction on fluid flow along the surface of an object, what aerodynamicists call boundary conditions. This required highly complex nonlinear partial equations developed independently in the first half of the 19th century by Claude Louis Navier and George Gabriel Stokes. Equations that accounted for interdependent variables such as pressure, density, and velocity. These became known as the Navier-Stokes equations, and they are among the most important and most difficult equations in all of fluid dynamics. During the late 19th century, advances in thermodynamics would lead to an energy equation for high-speed fluid flows that also would be needed later in aerodynamics. Unfortunately, the Euler and Navier-Stokes equations had no general analytical solutions when applied to practical problems like airflow over a wing, at least not without simplifying selected factors to permit linear solutions that might or might not represent reality accurately. The promise of computational fluid dynamics was that it could replace the partial derivatives or integrals in these equations with discrete algebraic forms. The data processing capability of high-speed computers could repeatedly generate flow field values for each variable at specific points in space and time, known as grid points, with results improving with each iteration as the solution converged. The end products, although not classic standalone mathematical solutions in the traditional sense, would be of great practical use for aerodynamic design purposes, including, as would be seen, shockwave calculations. Although the revolutionary potential of CFD was still some years in the future in 1975, 2 of the 52 papers presented at that conference introduced computer programs of particular value for sonic boom minimization. A NASA-sponsored paper by Richard Seabass and 3 colleagues at Cornell reported on several recent advances in sonic boom theory and introduced an easy-to-use computer program for aerodynamic minimization calculations. This program had been written by Joseph Liut Lung as his master's thesis, turning sophisticated theory into practical software that engineers could actually use. The other relevant paper came from Harris Hamilton of Langley, working with Frank Marconi and Larry Yeager of the Grumman Aerospace Corporation. They reported a new technique for accurately and efficiently computing high-speed inviscid, frictionless, flows in 3 dimensions around real airframe configurations. Although this research had been prompted by NASA's need to understand the aerodynamics of the Space Shuttle orbiter during its return flights from space, their innovation could be applied to all supersonic and hypersonic vehicles. NASA published full details on the procedure and its related computer code the following year, making it available to the broader research community. These tools, the minimization code from Cornell and the 3-dimensional flow solver from Langley and Grumman, represented important steps forward in the ability to predict and potentially optimize sonic boom signatures. They weren't complete solutions. They required significant expertise to use properly, but they moved the field forward, enabling calculations that had been impossible or impractically time-consuming just a few years earlier. Christine Darden's breakthrough. By 1975, a relatively young researcher at NASA Langley named Christine Darden had developed an innovative computer code specifically for use in sonic boom minimization. This was significant work, though it might have seemed like just another technical report at the time. Darden wrote the code to convert the Seabass-George minimization theory, which was based on an isothermal, uniform atmosphere, into a program that applied to the real stratified atmosphere, where temperature and pressure changed with altitude in complex ways. She accomplished this with new equations for calculating pressure signature changes, ray tube areas, and acoustic impedance in a realistic atmosphere. Although reliance on an isothermal atmosphere allowed reasonable estimates of sonic boom signatures for many conditions and greatly simplified the mathematics, Darden's modification offered more accurate equivalent area distribution calculations. This was particularly important for aircraft flying at low Mach numbers and for designing better aerodynamics in the nose area, goals she would continue to pursue throughout her career. Christine Darden's path to becoming NASA's top sonic boom expert was not straightforward, and it reflected both the barriers she faced and her determination to overcome them. She had earned a mathematics degree with highest honours from Hampton Institute in 1962, then taught high school for several years before beginning her career at Langley in 1967. She arrived as one of the last generation of what NASA called human computers, mostly women, many of them African American, who performed complex calculations by hand or with mechanical calculators to support engineering research. Darden worked in the computer pool for 6 years, an experience that gave her deep insight into the kinds of calculations engineers needed and the problems they were trying to solve. But she wanted to do more than perform calculations designed by others. She wanted to design the calculations herself, to formulate the problems, to pursue the solutions. In 1973, she did something that took considerable courage. She asked a director at NASA why men and women with the same qualifications were placed in such different jobs, men in engineering sections and women in computing pools. The director's response was telling. He looked at her and said that nobody had ever asked that question before. Darden replied simply, "Well, I'm asking it now." A few weeks later, she was transferred to an aerospace engineering team. Her first assignment was to write a computer program for sonic boom prediction and analysis. That assignment launched what would become a 30-year career in flight research, specializing in supersonic noise characterization, analysis, and reduction. Even as she began producing important research results, Darden continued her education. She earned a master's degree in mathematics from Virginia State College in Petersburg in 1978. Then she pushed further, earning a doctorate in mechanical engineering with a specialization in fluid mechanics from George Washington University in 1983. She was balancing full-time work at NASA, continuing education, and raising a family. It required extraordinary dedication and capability. Darden's 1975 code for applying minimization theory to real atmospheres represented a significant technical contribution, but it was just the beginning of her work in the field. She would become the leading expert at NASA on sonic boom minimization, developing design tools, conducting wind tunnel experiments, validating theories, and training others in the techniques. In 1989, she was named Technical Leader of NASA's Sonic Boom Group, a position that put her at the forefront of American research in this area during a crucial period. She would eventually become the first African-American woman at Langley to be promoted into the Senior Executive Service, the top rank in the Federal Civil Service. Before retiring in 2007, as Director of the Office of Strategic Communication and Education, she authored more than 50 publications in the field of supersonic flight, including seminal papers on sonic boom prediction and minimization, high-lift wing design, and flap design for supersonic aircraft. Her story would later be featured in the book Hidden Figures, which brought long overdue recognition to the contributions of African-American women mathematicians and engineers at NASA. But in 1975, she was simply a researcher doing important work that few people outside the specialized field would ever hear about, developing tools that might or might not ever be used to design actual aircraft. The Paradox and the Conference. Christine Darden and Robert Mack presented a paper on current sonic boom research at the first SCAR conference held at Langley from November 9th to 12, 1976. The timing was significant. The conference took place after both the Concorde and the Soviet Tu-144 had begun scheduled supersonic flights, though because of their sonic booms, both were restricted to routes over oceans and sparsely populated land areas. The dream of routine supersonic passenger service was now a reality, but it was a heavily constrained reality. Theirs was the only paper on the sonic boom issue among the 47 presentations at the conference. Only one paper out of 47. That stark ratio reflected how the research priorities had shifted. In other areas, NASA and its industry partners were making significant advances over the Concorde and Tu-144. They were developing quieter engines, improving fuel consumption, achieving better lift-to-drag ratios, creating lighter and stronger airframe structures using new titanium fabrication processes, and projecting direct operating costs that were estimated at 50% lower than the Concorde's. These were impressive achievements. They suggested that a second-generation supersonic transport could be economically viable and environmentally responsible in terms of noise and emissions. But there was one major problem left unsolved, one challenge that all the other advances couldn't overcome: the sonic boom. And because of the FAA's ban, this problem couldn't be addressed through better design alone. It would require changing the regulations, and that would require solving both the technical problem and the political problem. Darden and Mack's paper described what they called the low-boom, high-drag paradox. Contrary to earlier beliefs, they explained, it had now been found that improved efficiency and lower sonic boom characteristics did not always go hand in hand. Both theory and experiments had shown that an aerodynamically efficient sharp-nosed supersonic airframe generated a weaker bow shock than one with a less streamlined nose, which is exactly what you'd expect from basic aerodynamic principles. Yet with a blunt nose section, there was less propensity for the strong shock waves generated along the rest of the airframe, from the wings, the engines, the tail, to merge with the bow shock and create the typical N-wave sonic boom at the surface. The blunt nose created a strong initial shock, but that shock didn't strengthen as much as it propagated through the atmosphere. Unfortunately, the excess drag of a truly blunt-nosed supersonic aircraft would make it aerodynamically unacceptable. You'd burn too much fuel. The range would be too short. The economics wouldn't work. This was a genuine paradox, a case where two desirable goals seemed to contradict each other. The two Langley researchers were exploring ways to deal with this dilemma, though they acknowledged that a full solution would require extensive trade-off studies by engineering design teams working on actual aircraft projects. Meanwhile, they reported on preliminary results of their ongoing experiments using Darden's revision of the George Seabass methodology to design lower boom wind tunnel models that didn't pay too great a penalty in aerodynamic efficiency. They were trying to find the sweet spot, the compromise that would give acceptable boom characteristics without unacceptable drag. It was delicate work, requiring careful attention to the distribution of volume and lift along the entire length of the aircraft. Small changes in shape could have significant effects on both drag and boom intensity. The challenge was to understand those effects well enough to make informed design choices. As for the still critical question of what would constitute an acceptable sonic boom, the only research being done in North America at that time was at the University of Toronto. The Institute for Aerospace Studies there was testing humans, animals, and materials with various sonic boom simulators. They were also researching focused booms, effects of turbulence, and signatures in the shadow zone where the boom was partially blocked by terrain or atmospheric conditions. This work was valuable, but it was limited in scope and not directly connected to any aircraft development program. What was really needed was a large-scale human response study with thousands of participants exposed to carefully controlled boom signatures of various types. But who would fund such a study when there were no plans to actually build a supersonic aircraft that would fly over populated areas? It was a chicken and egg problem that wouldn't be resolved for decades. Practical tools and space shuttle booms. Another NASA contribution to understanding sonic booms came in early 1978 with the publication of Harry Carlson's Simplified Sonic Boom Prediction. This was essentially a how-to guide on a relatively quick and easy method to determine sonic boom characteristics in a standard atmosphere. It could be applied to a wide variety of supersonic aircraft configurations, as well as spacecraft at altitudes up to 76 kilometers, and could cover the entire width of a boom carpet. Although his clever series of graphs and equations did not provide the accuracy needed for predicting booms from maneuvering aircraft, or for designing airframe configurations, Carlson explained that for many purposes, including preliminary engineering studies or environmental impact statements, sonic boom predictions of sufficient accuracy could be obtained using a simplified method that didn't require a wind tunnel or elaborate computing equipment. Computational requirements could in fact be met by handheld scientific calculators or even slide rules. This was engineering at its most practical. Not every problem required a supercomputer. Sometimes what was needed was a method that any competent engineer could apply quickly to get a good enough answer. This procedure would be especially helpful to the armed services in preparing recently required environmental studies for areas where military aircraft flew supersonically. The military still had the right to create sonic booms over American territory when necessary for training or operations, but they now had to assess and document the impacts. Although the SCR program was drawing funds and attention away from aeronautics research, one aspect of NASA's space transportation system led to additional sonic boom research involving the full range of shock waves, from hypersonic speeds at the top of the atmosphere down to transonic speeds near the surface. In April 1978, NASA headquarters released its final environmental impact statement for the Space Shuttle program. This document benefited greatly from the agency's previous research on sonic booms, including extensive work done during the X-15 and Apollo programs, as well as the adaptations of Charles Thomas's waveform-based computer program. While the entire space transportation system was ascending, the environmental impact statement estimated maximum overpressures of about 6 pounds per square foot, about 40 miles downrange over open water, possibly reaching up to 30 pounds per square foot with focusing effects. These booms would be caused by both the long exhaust plumes from the solid rocket boosters and main engines, which acted somewhat as a phantom body extending behind the vehicle, and by the shuttle's curving flight profile while accelerating toward orbit. The trajectory would focus the shock waves in some areas while spreading them out in others, creating complex patterns that required sophisticated analysis to predict. During re-entry of the orbiter, the sonic boom was estimated at a more modest 2.1 pounds per square foot, comparable to the Concorde, which would affect about 500,000 people as the orbiter crossed the Florida Peninsula, or about 50,000 people when landing at Edwards Air Force Base in California. These were significant numbers of people being exposed to sonic booms, but NASA argued that the exposure would be infrequent enough, a few times per year at most, to be acceptable. In the following decades, as populations in those areas grew dramatically, millions more would hear the sonic booms of returning space shuttles. More than 120 of these returns would be monitored for their sonic boom signatures, creating an invaluable database of measurements under a wide variety of atmospheric conditions. The shuttle program, whatever its other accomplishments and problems, made a significant contribution to sonic boom science simply by providing repeated opportunities to measure real booms from a real vehicle under real conditions. Some other limited experimental and theoretical work on sonic booms continued in the late 1970s, even though it was no longer based on developing an American supersonic transport. Richard Seabass delved deeper into the tricky phenomena of caustics and focused booms. A caustic is a region where acoustical rays converge, like light rays focused by a lens, creating an area of much higher boom intensity than would otherwise occur. French researcher Jean-Pierre Guiraud had written the governing equations and derived a related scaling law, providing the theoretical foundation. After a numeric solution of Seabass's ideas by one of his graduate students, Kenneth Plotkin, who had begun working for Weil Laboratories in 1972 after receiving his doctorate from Cornell, applied these techniques to analyzing predicted focused booms from the Space Shuttle for the Marshall Space Flight Center. This work was part of the studies that went into the environmental impact statement described earlier. At the end of the decade, Langley's Raymond Barger published a study on the relationship of caustics to the shape and curvature of acoustical wavefronts caused by aircraft maneuvers. To display these effects graphically, he programmed a computer to draw simulated three-dimensional line plots of acoustical rays in the wavefronts, creating visualizations that helped researchers understand the complex geometry involved. One of his figures showed how even a simple decelerating turn, in this case from Mach 2.4 to Mach 1.5 in a radius of 14.3 miles, could merge the rays into the kind of caustic that might cause a superboom with several times the normal intensity. This kind of analysis was important for understanding what operational restrictions might be needed to prevent unacceptably strong focused booms from reaching populated areas. The mystery booms and continued research. Unlike in the 1960s, there was little if any NASA sonic boom flight testing during the 1970s using dedicated research aircraft. As a case in point, NASA's YF-12 Blackbirds at Edwards Air Force Base, where the Flight Research Center was renamed the Dryden Flight Research Center in 1976, flew numerous productive supersonic missions in support of the AST/SCAR/SCR program, but none of them were dedicated to sonic boom issues. The research focused on other aspects of high-speed flight: propulsion, structures, aerodynamics, control systems. On the other hand, flight testing of the Concorde provided some new sonic boom data from a real supersonic transport operating in actual airline service. An Anglo-American aeronautical conference in London in early June 1973, just a few weeks after the FAA's new rule prohibited civilian supersonic flight in the United States, included an informative paper on sonic boom measurements and their effects on people, buildings and wildlife during Concorde test flights along Great Britain's west coast. Once these swift new airliners became operational, however, most of their supersonic flying was done over the open ocean, where there was presumably only limited opportunity for gathering sonic boom data. The aircraft would accelerate to supersonic speeds after reaching the water and decelerate back to subsonic speeds before reaching land on the other side of the Atlantic. This was the operational compromise that made the Concorde economically feasible despite the boom restrictions. One strange and unexpected discovery about secondary booms came after British Airways and Air France began regular Concorde service to the United States. The first route was to Dulles International Airport near Washington, D.C. in May 1976. Then, after much local opposition due mainly to jet engine noise rather than sonic booms, service began to New York's Kennedy International Airport in November 1977. Although the Concorde slowed to subsonic speeds while well offshore, residents along the Atlantic seaboard began hearing what were called the East Coast mystery booms. These were detected all the way from Nova Scotia to South Carolina. Some of them were strong enough to be measurable on seismographs, which suggested they weren't just subjective experiences or misidentifications of other sounds. Although a significant number of these sounds defied explanation, and probably came from various sources including military activity, meteors, and unknown natural phenomena, studies by the Naval Research Laboratory, the Federation of American Scientists, a committee of the Defense Department's Jason Scientific Advisory Group, and the FAA eventually determined that most of the low rumbles heard in Nova Scotia and New England were secondary booms from the Concorde. These sounds were caused by distorted shock waves being bent or reflected by temperature variations high up in the thermosphere, while Concordes were still about 75 to 150 miles offshore. The shock waves would propagate upward and outward from the aircraft, reach altitudes of perhaps 50 or 60 miles, where temperature and wind conditions were just right, and then bend back downward to reach the coast. By the time they arrived, they had travelled far enough and been distorted enough that they sounded quite different from normal sonic booms, more like distant thunder or mysterious rumbling rather than sharp cracks. In July 1978, the FAA issued new rules prohibiting the Concorde from creating sonic booms that could be heard in the United States. Although the FAA did not consider that this ban applied to secondary booms, because of their low intensity, the affair made the FAA even more sensitive to the sonic boom potential inherent in any supersonic aircraft design. It reinforced their conviction that the ban on overland supersonic flight was necessary and appropriate. As part of the Naval Research Laboratory investigation into the East Coast mystery booms, NASA researchers Harvey Hubbard and Dominic McLean made an interesting discovery. They determined that Aerospace Defense Command F-106 interceptors scrambled from Langley Air Force Base to intercept Soviet Tu-20 Bear long-range bombers flying along the Atlantic coast on their regular flights to or from Cuba, created many of the sonic booms heard farther south from Virginia to the Carolinas. The Cold War was literally making noise along the American coast, though few civilians understood what they were hearing. At Langley, Christine Darden and Robert Mack continued to pursue their research on sonic boom minimization during the late 1970s, even though it was no longer a priority for the main SCAR program. Using the Seabass-George procedure as modified for a stratified atmosphere, they followed up on the previously described studies by Edward Kane's team at Boeing and, in particular, the studies by Harry Carlson's team at Langley. They used wing analysis and wave drag area rule computer programs, including viscous effects that earlier studies had often ignored, to help design 3 specially shaped wing body models with low boom characteristics for comparison with 2 of Carlson's models that had been designed mainly for aerodynamic efficiency rather than boom reduction. One of their new models was configured for cruise at Mach 1.5, the lowest speed for a truly supersonic transport, and 2 for cruise at Mach 2.7, which approached the upper limit for applying near-field sonic boom theory. At 6 inches in length, these were the largest models yet tested for sonic boom propagation within the confines of the Langley 4-foot by 4-foot unitary plan wind tunnel. This was an improvement made possible by continued progress in applying the ARAP code to extrapolate near-field pressure signatures measured in the tunnel to far-field signatures that would be heard on the ground. The low-boom models showed much more reduced overpressure than the standard unconstrained delta wing model and significantly lower overpressures than the unconstrained arrow wing design, especially at Mach 1.5, where the tail shocks were softened as well as the nose shock. The low-boom model's pressure signatures also showed definite flat-top characteristics rather than the typical N-wave shape. This was exactly what the theory had predicted, but seeing it confirmed experimentally was important. Darden and Mack first presented their findings at an American Institute of Aeronautics and Astronautics conference in March 1979. They published them in a NASA technical paper that October and in an article in the Journal of Aircraft in March 1980. These papers would become important references for future research, even though at the time they seemed to be the end of a line of inquiry rather than the beginning. To Christine Darden, it had become obvious through this work that because extreme nose bluntness produced large drag, a method of relaxing the bluntness was needed to offer the opportunity for compromise between blunt nose low boom and sharp nose low drag configurations. She wrote about this challenge in another NASA technical paper published in 1979 titled Sonic Boom Minimization with Nose Bluntness Relaxation. The paper focused on findings that because the shape of the aircraft influenced the shape of a midfield pressure signature, aircraft shaping had become a powerful tool in reducing the sonic boom. Using numerous equations and a computer code that NASA had sponsored Grumman to develop for calculating supersonic and hypersonic inviscid flow around various configurations, she explored theoretical options for eliminating the Bose shock, allowing unrestricted tail shock, and eliminating both shocks through careful design. Her calculations showed how to relax a blunt nose into a more conical shape to reduce drag without completely losing the boom reduction benefits of bluntness. Thus, she concluded, the boom levels could be reduced significantly without prohibitive drag penalties by defining the proper ratio of the shockwave spike width along the front of the fuselage relative to the entire equivalent length of the airplane. It was a delicate balance, but her work showed it was achievable with proper design. Although premised on airliner-sized supersonic aircraft, Darden and Mack's rather solitary work in the late 1970s on how carefully designed airframe shaping could in turn shape the signature of a sonic boom would help set the stage for future research on various sized supersonic aircraft. Because of funding limitations, however, this promising approach could not be sustained beyond 1979. It was apparently the last significant NASA experimentation on sonic boom minimization for almost another decade. Yet by validating the Seabass-George minimization theory and verifying design approaches for sonic boom reductions, their findings would serve as a point of departure when such research finally did resume. The aerodynamic design characteristics for boom minimization that they had confirmed, highly swept wings positioned aft, positive dihedral, carefully designed nose sections, attention to volume and lift distribution, would become the foundation for later low-boom designs. The last conference and visions of the future. The second conference on supersonic cruise research, held at Langley in November 1979, was the first and last under its new shortened name of SCR, rather than SCAR. More than 140 people from NASA, other government agencies, and the aerospace industry attended. They came to hear about the progress made over nearly 8 years of focused research and to discuss the implications for future supersonic aircraft development. This time there were no presentations on the sonic boom, not one. That absence spoke volumes about how thoroughly the research priorities had shifted since the first conference 3 years earlier. But in other areas, the results presented were impressive. The program had made significant advances in understanding supersonic aerodynamics, developing lighter and stronger structures, improving propulsion systems, and reducing other environmental impacts like engine noise and stratospheric emissions. The SCR program had demonstrated that a second-generation supersonic transport could be developed with far better characteristics than the Concorde in almost every measurable way except for the sonic boom. Fuel efficiency would be dramatically better. Range would be longer. Passenger capacity could be greater. Operating costs would be lower. Environmental impacts from noise and emissions would be reduced. These weren't just theoretical projections, they were backed by extensive research, wind tunnel testing, and component demonstrations. Robert Kelly from North American Rockwell did put forth an intriguing concept at this conference: a Mach 2.7 business jet for 8 to 10 passengers, or possibly a military aircraft that could generate a sonic boom of only 0.5 pounds per square foot. This was half the intensity that had been discussed as a potential goal for large transports. He proposed an alternate development path. Because of the difficulty of developing a big supersonic airliner in one step, why not validate the critical supersonic technologies in a small research vehicle first, prior to building a full-size supersonic vehicle? But, he asked, would such a research vehicle have only one use? Why not give it additional capability for military use or as a supersonic business jet? It was an interesting proposition. The concept he presented used a blended variable camber arrow wing and body design with fiber-reinforced titanium structures built using superplastic forming and diffusion bonding, advanced manufacturing techniques that promised lighter, stronger structures than traditional methods. The propulsion could use either of 2 different engine systems that had been developed under the SCAR program. The basic configuration represented sophisticated aerodynamic thinking, with every element of the design contributing to both performance and low boom characteristics. Although it wasn't proposed as a business jet per se, the concept suggested that supersonic business aviation might be achievable with low enough boom levels to potentially gain regulatory approval. Boeing had also submitted a study in 1977 on building a subscale demonstrator, 93 feet long, capable of Mach 2.4, that would test numerous characteristics and capabilities including sonic boom acceptability and possible boom-reducing modifications. The idea was to build something that could actually fly, not just sit in a wind tunnel, and use it to validate both the technologies and the design approaches that had been developed. These concepts pointed toward a possible future. It would take another 20 years for ideas about either a low-boom demonstrator or a supersonic business jet to go anywhere beyond paper studies. But the seeds were being planted. People were starting to think about supersonic flight, not just in terms of large airliners serving major city pairs across oceans, but in terms of smaller, more flexible aircraft that might be able to operate in ways that would be more acceptable to regulators and the public. Despite the SCR program's relatively modest cost, versus its significant technological accomplishments, the program suffered a premature death in 1981. The reasons were multiple and interconnected. The discouragingly high cost of Concorde operations demonstrated that even a flying supersonic transport wasn't automatically economically successful. Opposition to civilian research and development spending by some key officials in the new administration of President Ronald Reagan reflected a broader philosophical shift toward reducing government's role in technology development. The growing federal deficit made everything discretionary look vulnerable. These factors, combined with massive cost overruns for the Space Shuttle program that were consuming an ever larger share of NASA's budget, forced the agency to make painful choices. NASA abruptly cancelled supersonic cruise research without even funding completion of many final reports. It was an inglorious end to nearly a decade of solid work. As regards sonic boom studies, however, an exception to the premature termination was a compilation of useful charts for estimating minimum sonic boom levels for various combinations of aircraft length, weight, altitude, and Mach numbers that Christine Darden published in 1981. This final contribution from the program provided practical tools that engineers could use for preliminary design studies. The charts distilled years of research into a form that was immediately useful, even though there was no immediate application for them. Legacy and lessons. The story of supersonic cruise research from 1971 to 1981 is a story of persistence in the face of obstacles, of scientific progress despite political setbacks, of researchers who continued working on problems even when the practical applications seemed distant or impossible. It's a story that teaches important lessons about how aerospace technology development actually works. The cancellation of the SST program in 1971 could have been the end of American supersonic research. Instead, it became a transformation. The work continued, more focused, more scientifically rigorous, less driven by political deadlines, and more driven by a genuine desire to understand the fundamental physics and engineering challenges involved. The researchers involved in the AST/SCAR/SCR program made fundamental contributions to sonic boom theory and prediction. The work of George and Seabass, refined and extended by Christine Darden and others, created mathematical frameworks that are still used today. The computer codes developed by Charles Thomas, Wallace Hayes, and others became the foundation for modern boom prediction tools. The wind tunnel techniques developed at Langley and other centres established methods that are still employed. Perhaps most importantly, the program validated that low boom designs were possible. The wind tunnel tests conducted by Darden and Mack proved that careful attention to aircraft shaping could produce significantly reduced sonic boom signatures. The signatures weren't silent, but they were dramatically quieter than conventional supersonic designs. This demonstrated that boom minimization wasn't just a theoretical exercise, it was an achievable engineering goal. The FAA regulation that banned measurable sonic booms over the United States in 1973 seemed at the time like the death knell for supersonic civil aviation in America. In retrospect, it can be seen as something more nuanced. It established a clear standard. If you want to fly supersonically over American territory, you need to eliminate or dramatically reduce the boom. That standard seemed impossible to meet with 1970s technology, but standards can drive innovation. They create a target for researchers and engineers to aim at. The economic challenges that killed the SST program and limited the success of the Concorde were real. Supersonic flight burns more fuel per passenger mile than subsonic flight. The aircraft are more expensive to build and maintain. The operational constraints are greater. These factors didn't go away when the AST/SCAR/SCR program started, and they didn't go away when it ended. They remain challenges today. But technology advances, Materials get lighter and stronger, engines become more efficient, design tools become more sophisticated, manufacturing techniques improve. What's economically impossible in one era becomes marginally viable in the next and fully commercial in the era after that. The research conducted in the 1970s created knowledge and tools that would be essential when supersonic aviation development resumed decades later. The people involved in this research often worked in obscurity. Few Americans knew who Christine Darden was in the 1970s. Few had heard of Ed McLean or Robert Mack or Harry Carlson or any of the other researchers labouring away at Langley and Ames and in university labs and industry wind tunnels. They weren't building hardware that could be photographed and admired. They were developing theory, writing code, testing models, publishing papers that only specialists would read. This is how progress actually happens in aerospace engineering. It's not usually dramatic. It's usually incremental, methodical, built on careful work by dedicated professionals who may not see the fruits of their labour for years or decades. The drama comes later, when someone builds something spectacular based on their work, but the real foundation is laid in quieter times, in research programs that might not even seem successful by conventional measures. The AST/SCAR/SCR program ended in 1981 without producing a new supersonic transport. By that measure, it might seem like a failure, but it produced something more durable than an aircraft. It produced knowledge. It trained researchers. It developed tools. It validated theories. It demonstrated possibilities. And when the time came, decades later, for a new generation of supersonic aircraft development, researchers would return to the work done in the 1970s. They would use the codes, apply the theories, follow the design principles, and build on the foundation that had been established. The story of sonic boom minimization research is far from over. In fact, in many ways, it was just beginning during the period we've been discussing. The regulatory environment would eventually change. NASA would resume focused sonic boom research. Industry would develop new supersonic aircraft concepts. Flight demonstrators would prove that low boom designs could actually work in practice, not just in wind tunnels and computer simulations. But all of that future work would rest on the foundation laid during those 9 years, from 1972 to 1981. When researchers in the 21st century write computer codes to predict and minimize sonic booms, they use algorithms descended from the work of Thomas and Hayes and Darden. When they design low-boom aircraft, they apply principles developed by George and Seabass and refined by the SCAR program researchers. When they validate their designs, they use techniques developed at Langley and other NASA centers during this era. The quest to quiet the boom didn't end when the SCR program was cancelled. It was merely interrupted. The knowledge remained. The tools remained. The people who understood the problems and had ideas about solutions remained in the field, many of them training new generations of researchers and engineers. And when the time was right, when the political and economic conditions aligned, when the technology had advanced far enough, the quest would resume. Conclusion: the long arc of progress. As we reach the end of this story, it's worth reflecting on what we've learned about how aerospace innovation actually works. The path from President Nixon calling the SST cancellation the #1 technological tragedy of our time, to the establishment of the Advanced Supersonic Technology program, to its eventual death as the Supersonic Cruise Research Program in 1981, was not a simple trajectory. It was filled with setbacks and breakthroughs, political obstacles and scientific advances, disappointed hopes and validated theories. The researchers who worked on sonic boom minimization during these years probably didn't feel like they were doing world-changing work most of the time. They were solving equations, running wind tunnel tests, writing computer code, publishing papers that few people would read. The glamour had gone out of supersonic research when the SST was cancelled. The public attention had moved on to other things. The funding was modest and always uncertain, but they kept working because that's what researchers do. They kept pushing the boundaries of knowledge because questions remained unanswered. They kept developing tools and techniques because they believed, or at least hoped, that someday those tools would be needed. And they were right. The legacy of the AST/SCAR/SCR program extends far beyond its official 9-year lifespan. The theoretical frameworks developed by Albert George and Richard Seabass and extended by Christine Darden and others remain fundamental to sonic boom research today. The computer codes written in the 1970s, primitive by modern standards, established approaches that evolved into sophisticated modern prediction tools. The wind tunnel techniques developed and refined during this period are still used. The design principles validated through those wind tunnel tests inform current low-boom aircraft concepts. Christine Darden's particular contribution deserves special recognition. She broke barriers not just as an African-American woman in a field dominated by white men, but as a scientist who made fundamental contributions that advanced the entire field. Her work on adapting boom minimization theory to real atmospheric conditions, her insights into the low-boom high-drag paradox, her development of practical design tools, these would have been significant accomplishments for anyone. That she achieved them while also breaking down institutional barriers makes her story particularly remarkable. The story of this era in supersonic research reminds us that progress in aerospace engineering isn't linear. It's not a steady march forward. It's a process of starts and stops, of investment and disinvestment, of periods when everything seems possible followed by periods when nothing seems achievable. The SST program soared on waves of political support and then crashed when that support evaporated. The SCAR program emerged from those ashes but could never escape the shadow of the FAA's 1973 regulation. Knowledge accumulated, capabilities grew, but without a path to application, the program couldn't survive budget pressures and political indifference. Yet the work wasn't wasted. When NASA began developing the X-59 quiet supersonic demonstrator in the 21st century, researchers returned to the sonic boom minimization studies of the 1970s. When Boom Supersonic and other companies started designing new supersonic aircraft, they applied principles that had been validated decades earlier. When regulators began reconsidering the ban on overland supersonic flight, they had data and analysis from this earlier era to inform their decisions. The quest to quiet the boom, to make supersonic flight acceptable over populated areas, continues. It has outlasted individual programs and political administrations. It has survived budget cuts and regulatory barriers. It persists because the fundamental challenge remains. How do you design an aircraft that can fly faster than sound without creating unacceptable noise on the ground? The physics haven't changed. The mathematics haven't changed. What has changed is our ability to apply that physics and mathematics through better design tools, better materials, better manufacturing techniques, better propulsion systems. The researchers of the 1970s gave us the foundation. They showed what was possible in theory and validated it in wind tunnels. They developed the tools to predict boom signatures and optimize designs. They demonstrated that low boom configurations could be achieved without prohibitive drag penalties. They established the knowledge base that would be essential when the economic and political conditions finally aligned to support renewed development. That's the real legacy of the AST/SCAR/SCR program. Not aircraft that were built, but knowledge that was created. Not products that were sold, but capabilities that were developed. Not immediate success, but essential preparation for future success. In aerospace engineering, as in many fields, the most important work is often the work that enables someone else's breakthrough years or decades later. As you think about the future of supersonic flight, about the X-59 demonstrator and the business jets under development, and the potential return of supersonic airliners, remember the researchers of the 1970s who kept the dream alive during lean years. Remember Christine Darden and Ed McLean and Robert Mack and Harry Carlson and all the others whose names don't appear in history books, but whose work made history possible. Remember that progress isn't always obvious when it's happening. Sometimes the most important advances look like failure at the time. The quest continues. The boom hasn't been fully quieted yet, but every advance brings us closer to the goal. And when that goal is finally achieved, when supersonic aircraft routinely fly over land without disturbing the people below, it will be built on foundations laid 5 decades earlier by researchers who never gave up on the dream of faster, quieter flight. If you enjoyed this deep dive into the history of supersonic research and sonic boom minimization, please consider hitting that like button and subscribing to the channel. There are so many more fascinating stories from aerospace history to explore. Stories of dedicated people working on difficult problems. Stories of setbacks and breakthroughs. Stories that remind us that progress in technology is built on the patient work of generations of researchers and engineers. Until next time, keep looking up and keep wondering about the future of flight.